Good day, everybody. Once again, we're back together. All right, and today we're looking at the ideal gas equations. Of course, we've been busy with gas laws. So if you haven't subscribed, please just make sure you're part of the family. All right, and well, let's have a look at it and dive right into it. Now, remember we spoke about ideal gases. So we've looked at, Gay-Lussac's law. We've looked at Boyle's law. We've looked at Charles's law. And we've looked at the combined gas laws, right? Now, in this case, when we're looking at the relationship between ideal gases, right, remember that we stated several things. We said, well, the ideal gases, first of all, occupy no volume, right? So ideal gases would occupy absolutely no volume. But secondly, what we know is that there are no forces between the particles. So if we were to get particles that are moving, right, and those are particles of an ideal gas, right? So we consider that the mass is so negligible that it is considered almost non-existent, right? So we also consider that in this case, the motion of the particles is in a constant manner, all right? So that in this case, obviously the motion is directly proportional to the temperature in this case, right? But now let's have a look at the equation itself, the ideal gas equation. First, we've got P, which is obviously for pressure, okay? And now, just a couple of things that I want to give a warning about. So ideally, we are going to give this in kilopascals. And if that is the case, please note that this volume has to be in cubic decimeters, right? Now, I'm going to write the other units in a different color so that you just remember. If it should ever happen that you have the gas in pascals, all right, then the volume must be in cubic meters. Okay, and of course, to convert from cubic decimeters to meters cubed in this case, all you do is you divide by 1,000. Okay, so the difference between this and that, okay, is just simply to divide by 1,000. Okay, and of course, to convert from kilopascals to pascals, on the other hand, you multiply by 1,000. Okay, right, so please keep in mind when pressure is in kilopascals, your volume should be in cubic decimeters. And if your pressure is in pascals, then your volume should be in meters cubed. Right, now let's look at the other variables in our equation. Right, so N in this case stands for the number of moles. Right, now please don't forget that number of moles in physics, or rather in physical science, if we are given mass, we can say, well, that's mass divided by molar mass, where molar mass, we get that from the periodic table. Right, and now R is the universal gas constant, and the value of R is 8.31. Okay, we call that the universal gas constant. So remember that you are always given that value for R. And of course, finally, we've got our temperature in this case, which temperature is measured or should be measured in Kelvin, right? So that we use the Kelvin scale. And please remember that Kelvin scale, to convert from degrees Celsius to Kelvin, all we do is to add 273 plus the temperature in degrees Celsius. Okay, right. So in this case, we're going to just try out some questions having to do with using the ideal gas equation. And I think what I will want to do finally is have a look at graphs. However, I will do that in the next video. All right, now let's have a look at it. Let's look at our first example. All right, so let's look at our first example. They say to us we've got a sealed jar. Okay, let's try to maximize it. They say a sealed jar whose volume is exactly 1 liter, right? Please remember that 1 liter is exactly the same as saying this is in cubic decimeters, right? Okay, so they say it contains 1 mole of air at a temperature of 20 degrees Celsius, right? Assuming that the air behaves as an ideal gas, so what is the pressure inside the jar in pascals? All right, now let's have a quick look at what information we're given. Right, so they told us that the volume, okay, so we're given the volume there as 1 liter or 1 cubic decimeter, right? And they said that the number of moles, that's 1, okay? And also the temperature is 20 degrees Celsius. But remember, if we want to convert it to Kelvin, we just add 273. And so that will be 293 Kelvin. Okay, right. And what we also have there, remember that the ideal gas constant in this case is 8.31. Please don't forget that you always have this value, right, with you. So now we need to calculate what the pressure is. So all we're going to do is go into our equation. PV is equal to nRT, right? So remember I said to you, when our pressure is in pascals, we want it in pascals. So it means that our volume must be in cubic decimeter, in meters cubed rather, cubic meters, right? So in this case, what I'm simply going to do, because I want pressure in pascals, I'm going to convert the volume 1 cubic decimeters. I'm going to divide that by 1,000, right? So remember, as I did say to you earlier on, if I want to convert from cubic decimeters to cubic meters, in this case, all I do is divide by 1,000. So this gives me 0.001, okay, cubic meters. So my pressure in this case is unknown, okay, multiplied by my volume, which is 0.001. Okay, that's 8.31. And, actually 1 mole, that's the number of moles, times 8.31. And that's multiplied by 293, which is our temperature. Okay, right. So all we need to do is divide both sides by 0.001. Okay, and what would be the pressure in that case? All right, so we're going to say this is 1 multiplied by 8.31 times 293. Okay, and we get 2,434.83, and we divide that by 0.001. Okay, so I get a pressure of, well, that looks like 2 million. And okay, so I can say this is 2.43 times 10 to the power 6. Okay, this is in pascals. All right, now of course, if you wanted to express that in kilopascals, what you could do is just simply divide that by 1,000, and in this case it would give you that pressure in kilopascals. All right, okay, I hope that makes sense. Let's go on to the next one and see if we can find some more applications on this. All right, let's go on to our second example. They say an unknown gas occupies 3.36 milliliters at STP. How many moles does the gas have? Right? So first of all, let's just clarify quickly, what is standard temperature and pressure, right? So when we are referring to standard temperature is said to be at 0 degrees Celsius. So of course, if we convert that to Kelvin, that would be at 273 Kelvin, right? But standard pressure, on the other hand, this is 1 atmosphere of pressure. Okay, so we can say this is 1 atm, which we approximate to be at 100 kilopascals. Of course, depending on the exam that you're writing, sometimes we actually become more specific. The actual value is 101.3 kilopascals, right? So this would be the amount in kilopascals. Now, if you didn't want to put the amount in kilopascals, of course, in this case, all you need to do is just multiply by 1,000, right? So what do we now say in terms of, STP? So remember, these are our values for STP, but we're going to actually look at what we do when we calculate number of moles at STP. First, I'm going to use the ideal gas equation, right? Let's try and find out what information are we given here, right? They said that the gas occupies that volume. So we know we've got a volume of 3.36 milliliters, right? We'll come back to the conversion. Please remember that we said that if your pressure is in kilopascals, then your volume has to be in cubic decimeters. If it's in pascals, then your volume in cubic meters, right? So now our volume is 3.36, right? We know our pressure. We said this is 101.3 kilopascals, all right? But we also know in this case the number of moles is exactly what we're looking for. But the ideal gas constant, that's 8.31, and the temperature would give us 273, right? Now we're calculating the number of moles. Now please, I want you to note, in this case our pressure is in kilopascals, which means this volume has to be in cubic decimeters. Now remember that cubic decimeters, or rather milliliters, are the same as cubic centimeters, right? Now, how do I convert from cubic centimeters to cubic decimeters? All I do to convert from that to the other, I need to divide by 1,000, right? So divide by 1,000. Okay, right. So in this case, it means that our volume after conversion becomes 3.36 divided by 1,000. Okay, so that becomes 0.00336. Okay, right, so that is in terms of our volume, right? Now let's put that in our ideal gas equation. PV is equals to nRT, right? We said our pressure is 101.3, okay, and we multiply that by our volume. Okay, which is equal to N. Now remember, N is the number of moles, right? So that's what we're looking for. But we know that R is 8.31 and temperature, we said, is 273. Right, so because we're looking for N, we're going to divide both sides by 8.31 times 273. Of course, what I do on the left, I would do on the right hand side. Okay, right, so what does our value for N give us, right? So we've got 101.3, right? That's in kilopascals, multiplied by 0.00336, right? And we divide all of that by 8.31. I'm going to put that in brackets, times 273, right? I seem to get a number of moles, 0.00015. Okay, so those are the number of moles of the gas. Now, what I want us to quickly do is to also use what we know about molar volume. Now, what is molar volume? In this case, when we talk about VM, the molar volume, this is the volume that any gas would occupy at a specific temperature and pressure, right? In this case, we're talking about STP, right? So at STP, I want you to know that our molar volume is 22.4 cubic decimeters per mole, all right? So that is the value that we always use. So now, how do we use the molar volume, right? So it means if I were to look for, in this case, the number of moles of any gas, it would be the volume that it occupies divided by the molar volume, right? Now we wanted to find out what the number of moles are, right? But in this case, we know the volume that the gas occupies, okay? We said the volume was 0.00336. And we divide that by the molar volume at STP. Please remember this is only applicable at STP to be 22.4 cubic decimeters, right? So let's see if we get approximately the same answer. 336, and this is now divided by 22.4. Right, I hope that you can see that we get exactly the same answer, which is 0.0015 moles. So that is how we use our molar equation in this case. So remember, at STP, what we would know is that molar volume, and the molar volume at STP is always 22.4. By the way, you're provided that value in your data sheet in your exam, okay? So please look out for it, okay? Right, so we're going to take one last example and I will wrap it up in terms of this video and we'll see each other again, all right? Right, so let's look at the third example. So they say to us we've got calculate rather the volume of at STP of a given mass of gas which occupies 200 cubic decimeters at a pressure of 260 kilopascals and a temperature of negative 13 degrees Celsius. All right. Now we're looking for the volume at STP. Now remember, we said the molar volume at STP is simply going to be 22.4 cubic decimeters, right? That is for 1 mole of any particular gas at STP. Now, what we need to do is find out, the number of moles, of course, of this particular gas. So we're not going to use the STP amounts for now, but we're going to now use the other information that was given, right? So what did they tell us? They told us that it occupies 200 cubic decimeters, right, when the pressure is 260 kilopascals and at that temperature. Right, so what do we know? So we know that the volume that it occupies is 200 cubic decimeters when the pressure 260 kilopascals. All right, I always take my cue from the pressure. So in this case, because my pressure is in kilopascals, I am definitely going to have my volume in cubic decimeters, so which means they are in the correct units. All right, now the number of moles, that's what we're looking for, right? And of course our ideal gas constant, which is 8.31, and the temperature, right? So in this case, our temperature value, all right, yeah, let's remove this guy over here out of the way, right? So in this case, we are going to say, well, our temperature is going to be minus 13 plus 273. Now, in this case, what does that give us? Well, it will give us 260 Kelvin. Okay, right. Now, We want to find out what is the number of moles, and so we use our equation, ideal gas equation. PV is equal to nRT, right? So a pressure value, that's 260, right, multiplied by 200, which is the volume. We're looking for the number of moles, that's 8.31, and 260 Kelvin. Right, so all we're simply going to do in this case, we're going to divide both sides by 8.31, not 8.3.1, 8.31 times 260, right? So that this cancels with that, but what we do on the right, we do on the left. So that's 8.31 times 260. Right, to pull out a calculator, say 260, actually, let's do this, 260 and 260 cancel. Okay, so we've got 200 divided by 8.31. Okay, I get 24, so the number of moles would be 24.06, or let's say 07, right? So those are the number of moles. Right, now we needed to find out how much volume, or the volume in this case, that these moles will occupy, okay, right, at STP. So what you can do is actually use ratio and proportion and simply say 1 mole of any gas at STP occupies 22.4 cubic decimeters, right? So the question is, if I've got 24.07 moles, okay, what would be the volume that it occupies? And all you do is cross multiply. V times 1, that's V, okay? And you can say this is 22.4 multiplied by 24.07, and in this case, if I take that value, okay, 22.4 multiplied by 24.07, and we get a volume of 539.17 cubic decimeters. Okay, right, and it only makes sense that, of course, I mean, if we had 1 mole, it occupies a smaller volume, but if we've got, I mean, 24.07, they should occupy a much larger volume than that. Okay, right, ladies and gents, we are going to keep looking at some examples. Of course, for now, I want to leave it here, right? But in fact, before I just leave this here, remember what you also could have done is use this equation, right? We said number of moles is volume divided by molar volume, right? We know that in this case, the number of moles was 24.07. Okay, we are looking for the volume, and we know the molar volume at STP is 22.4, right? And of course, if we cross multiply, V is equal to 22.4 times 24.07, which we get the same answer, which is 539.17 cubic decimeters. Okay, right, I think using this equation as well would be quite ideal when solving for these kind of questions. All right, so from me for now, ladies and gents, I'll see you guys next time. All right, please don't forget to subscribe and like, okay, and tell as many people that, hey, your favorite uncle is doing the most on YouTube. I'll see you guys next time. Sharp, sharp.